determine the minimum spacing of Wal-Pak units to achieve 1 lumen per square foot in a 40,000 square foot retail space, several factors must be considered. Firstly, the lumen output of the specific Wal-Pak units being used. Secondly, the mounting height. Thirdly, the reflectance of the ceiling, walls, and floor. And fourthly, the light loss factor, which accounts for dirt accumulation and lamp depreciation. Since the egress paths are generally determined by dividing the building into quadrants and directing occupants to the nearest exit within that quadrant, ensure that the lighting along this path meets or exceeds the minimum illumination requirements specified in relevant codes and standards. This is especially critical at exit doors, corridor intersections, and corridors with limited visibility. The first step is to determine the required lumens. Since you aim for 1 lumen per square foot, the total required lumens for the 40,000 square foot space is 40,000 lumens. Secondly, you need to select a Wal-Pak fixture. Wal-Pak fixtures come in a variety of lumen outputs. For example, a typical LED Wal-Pak might produce 10,000 lumens. You'll need to refer to the manufacturer's specifications for the exact lumen output of the fixture you intend to use. Thirdly, consider the mounting height. You mentioned mounting heights of either 10 feet or 8 feet. Low mounting heights will generally require closer spacing to achieve uniform illumination, while high mounting heights can allow for wider spacing. The spacing to mounting height ratio is a crucial factor in lighting design. Fourthly, estimate the coefficient of utilization or CU. The CU represents the efficiency of the lighting system in delivering light to the work plane. It depends on the room's dimensions, reflectance values of the ceiling, walls, and floor, and the fixture's light distribution characteristics. Lighting manufacturers typically provide CU tables for their fixtures, which can be used to estimate the CU for a given room. If you do not have access to these tables, it is acceptable to initially assume a CU of 0.6 or 60% for a space like this, but a more accurate value should be used in the final design. Fifthly, consider the light loss factor or LLF. The LLF accounts for the reduction in light output over time due to factors such as lamp depreciation and dirt accumulation on the fixtures. A typical LLF might range from 0.7 to 0.8. Next, calculate the number of fixtures needed. The formula for calculating the number of fixtures is number of fixtures equals total required lumens divided by fixture lumens multiplied by CU multiplied by LLF. For example, if you are using a Wal-Pak fixture with 10,000 lumens, and you estimate a CU of 0.6 and an LLF of 0.7, the number of fixtures would be 40,000 divided by 10,000 multiplied by 0.6 multiplied by 0.7, which equals approximately 9.52 fixtures. Since you cannot install a fraction of a fixture, you would need to round up to 10 fixtures. Now, determine the spacing. Divide the total area by the number of fixtures to find the area each fixture needs to cover. In this case, 40,000 square feet divided by 10 fixtures equals 4,000 square feet per fixture. To find the spacing, take the square root of the area per fixture. The square root of 4,000 is approximately 63.25 feet. This would suggest a grid spacing of about 63.25 feet by 63.25 feet. However, this is a preliminary calculation and assumes a perfectly uniform distribution, which is unlikely in practice. Now consider the rectangular shape of the building. Given the 200 foot by 200 foot dimensions, you can divide the building into a grid. With 10 fixtures, you could arrange them in a pattern that provides relatively uniform coverage. For example, you could place them in 2 rows of 5 fixtures each. The spacing between fixtures would be 200 feet divided by 5, which equals 40 feet along one axis, and 200 feet divided by 2, which equals 100 feet along the other axis. This would result in a spacing of 40 feet by 100 feet. Now consider mounting on top of walls. Mounting the Wal-Pak units on boxes on top of the walls at 10 feet or using cut-in boxes to lower them to 8 feet will affect the light distribution. Lower mounting heights will result in more concentrated light patterns, requiring closer spacing to avoid dark spots. Now consider exit sign placement. Exit signs are required at all exit doors, corridor intersections, and corridors with limited or restricted views such as zigzags. The placement and spacing of exit signs are governed by building codes and standards such as the National Fire Protection Association or NFPA 101 Life Safety Code. Ensure that the exit signs are clearly visible and provide an ambiguous direction to the exits. Now consider code compliance and local regulations. Since the project is in Phoenix, Arizona, it is essential to comply with all applicable building codes and regulations. While the city may be slow to respond, it is crucial to consult the relevant codes and standards to ensure compliance. These codes typically specify minimum illumination levels for egress paths, exit sign requirements, and other safety-related lighting provisions. To find the minimum spacing, consider the following approach. Firstly, obtain photometric data for the selected Wal-Pak fixture. This data provides detailed information about the fixture's light output and distribution characteristics. Secondly, use lighting design software to model the space and simulate the lighting performance. Software such as Sqft 32 or Dialux can help you accurately predict the illumination levels and uniformity based on the fixture's photometric data, mounting height, and room characteristics. Thirdly, perform a point-by-point calculation to verify that the illumination levels meet the required 1 lumen per square foot. This involves calculating the light contribution from each fixture at various points in the space. Fourthly, adjust the fixture spacing and locations as needed to optimize the lighting performance and ensure compliance with the code requirements. Now consider emergency lighting. In addition to the general lighting, emergency lighting is required to provide illumination in the event of a power outage. Emergency lighting must be powered by a backup power source such as a generator or battery system. The emergency lighting system should be designed to provide adequate illumination along the egress paths and at exit doors. Now consider uniformity ratio. Uniformity ratio is the ratio of the minimum illuminance to the average illuminance in a space. A good uniformity ratio ensures that there are no dark spots or excessive brightness variations. A typical uniformity ratio for a retail space might be 0.6 or higher. To calculate the uniformity ratio, firstly, measure the illuminance at several points in the space. Secondly, calculate the average illuminance by summing the illuminance values and dividing by the number of measurement points. Thirdly, find the minimum illuminance value among the measurement points. Fourthly, divide the minimum illuminance by the average illuminance to obtain the uniformity ratio. Now consider lighting controls. Lighting controls can help to reduce energy consumption and improve the overall lighting performance. Lighting control strategies include occupancy sensors, which turn off the lights when a space is unoccupied, daylight harvesting, which adjusts the lighting levels based on the amount of natural light available, and dimming controls, which allow the lighting levels to be adjusted to suit the needs of the occupants. In conclusion, determining the minimum spacing of Wal-Pak units to achieve 1 lumen per square foot requires careful consideration of the fixture's lumen output, mounting height, room characteristics, and code requirements. It is essential to use photometric data, lighting design software, and point-by-point calculations to optimize the lighting performance and ensure compliance with all applicable regulations. Additionally, exit signs must be properly placed to guide occupants to the exits in a clear and unambiguous manner.